Let's start with a simple little program. And I can't write. Today is starting good. Well, something like that. Let's close the bracket down here. Just for completion's sake. And our program will be... let's start with an integer that we declare. Let's call it C, and we start with 0. And we're going to declare a second integer, f, which is going to be... Let's do something more fancy. How would we involve C in this? So let's say C times 9 divided by 5 plus 32. Just completely random. Let's try to see what happens. Right, so we split this off again. So we have our table as usual, type, name, and value. And we'll start with first line. Let's skip the formalities and just go straight to what it is. We have the integer type, it's called C, and it's going to be set to 0. First instruction is done. The second instruction, a bit more interesting. Let's try to do that the old-fashioned way. F equals C times 9 divided by 5 plus 32. We have several different operations. We have the declaration, the assignment, multiplication, division, addition. These math operations do have precedence over these two, so we're going to operate on them first. Multiplication and division have priority over addition, so it's going to be one of those two, and they have equal precedence, so we go from left to right. We start with the multiplication. So next it's int f equals c, which micro operation, we look up the value, it's 0. And 0 times 9 is 0, divided by 5 plus 32. And then we continue with the division, and 0 divided by 5 is just 0 plus 32. Then it's int f equals 32. And now we have only the declaration and the assignment, which is just declare the variable, and f, and assign 32. And that operation is done. Bit more cleanup. And let's say we set this value now to 100, different number. And this time we're gonna use that to create a value for C. Let's make this a bit more complex. We start with f and subtract 32. And then we multiply this by 5 and divide by 9. It was pure coincidence, I'm sure. It looks very similar by pure coincidence. So we will continue with f equals 100. Let's not bother with that. It's just going to be 100 in here. Just the assignment, only a single operation. And now comes this part down here. C equals f minus 32 times 5 divided by 9. We have an assignment, subtraction, multiplication, division. And we have these brackets, which changes precedence. We have to start with this subtraction because it's inside the brackets. Basically, this entire part on the right follows the standard rules for math. So this is actually f minus 32. We look up f, 100. So this is 68 times 5 divided by 9. Now we have the assignment with the least precedence and just multiplication, division again, just like before. We start with the multiplication, so that's 68 times 5, 340 divided by 9. And next we have the division. 340 divided by 9 is... let's see, Okay, I'm just writing this out the way I would do it in my head. Next would be 360 divided by 9 minus 20 divided by 9, which itself is 80 divided by 9 plus 2 divided by 9. A bit convoluted, but bear with me. And this would be 40 minus 2 plus 0.2 repeating. So this is actually just minus 40 minus 2 minus 0.2 repeating. So 38 minus, and that would be 30. 37.7 repeating. Okay. There's an issue here. This is the correct result, I think. It should be. It looks correct. But we're using integer numbers here. We're working with integer numbers. It could be 37, just fine. It could be 38, just fine. It can't be anything in between. This 0.7 doesn't fit in our integer. So what do? When we have to limit something to an integer, what we usually do is we round the number, right? So we don't want any decimals, just round to the nearest integer. That's what you used to, though, so that would be 38. On C#, this happens as well, though rounding is a bit weird. In the simplest terms, we just remove anything behind the decimal. C is actually, with this assignment, 32. So you would be used to rounding up in this case because it's a 0.7. 0.5 and above would be rounded up to 38. But in this case we round down. But we don't always round down, we only round towards 0. So minus 37.7, repeating, would be actually rounded up to minus 37. But plus 37.7 would be rounded down towards 0, so 37. And if you work with integers, the simplest way you can think about it is just remove any decimals. Just strike them out, they don't exist anymore. Don't think about rounding. And just in case you haven't noticed this, these formulas are the conversion between the temperature units Celsius and Fahrenheit. So in the beginning we converted 0 degrees Celsius, freezing point of water, into Fahrenheit. And then we converted 100 degrees Fahrenheit, which should be body temperature, to Celsius, which was 37.7, which is also correct. Only 37 isn't the exact measurement. It's not actually 100 degrees Fahrenheit. We have an error in here. We have a difference between what the actual value should be, purely mathematical, and what we store in our program. There's discrepancy here. Specifically 0.7 repeating. And in general, with integer numbers, the error could be anything less than 1. Like even if you, like a 0.99999, this would still be rounded down towards 37 instead of up to 38. So we almost have up to 1 degree of error. Or an error of up to almost 1 degree. Be that Celsius or Fahrenheit, depends on which conversion you do. With the first one we got lucky because it's 0, so there was no error. It just worked out nicely. The first thing we could do to improve this to reduce the error at least, is to round properly. Instead of rounding towards 0, round towards the nearest integer. And there's a simple trick to do that with integers. In general, the formula you will encounter actually quite a lot. Though usually you would do that for things like division by 2. That's the most common place I use it in, but there's a general formula. If you have two integer values, a and b, and you divide a by b, and you want the result to be rounded to the nearest integer, not towards 0, you simply add half of b to a and divide that by b. Not 5. What am I doing? B. Looks a bit weird, but this way, if you think about it a different way, we move the value for a along. Actually, let me just write down some numbers. Should probably write this out. 7. Yeah, let's say we divide by 3, right? So divide by 3. The principle holds true for all combinations. This is just so you can visually see why this works. So with our rules for round towards 0, this would be 0, 0, 1, 1, 1, 2, 2. We divide by 3, but we drop all the decimal places. So this is the first division by 3. For 3 is the first we get actually a value out. That's not 0. And every third number we increase by 1. So this would be the result for straight up a divided by b. Now what we want, if we round towards the nearest integer, would be this is 0, true, but 2/3 should be 1 already. 3 divided by 3 should be 1, 4 divided by 3 should be 1, and 5 divided by 3 should be 2 when we round it. This should be 2, and this should be 2. And if you look at that, all that happens here is these numbers are the exact same numbers as for the straight up rules that happen in C#, just shifted up a bit. So what happens to C# is what we want to happen, just a bit later, further down. And if we take our value, our a, and just add a certain number of numbers to it, we effectively shift down which result we want. And when we shift it by exactly b half, so this would follow the roots for C#. So with this, we mean b divided by 2 rounded towards 0. So for 3, that's 1. For 3, that's 3 divided by 2, which will result in 1. 1.5, you drop the decimals, you end up with 1. So we shift a by 1. So when we divide this by 2, for 1 divided by 3, what we're actually calculating would be 2 divided by 3. And for a equals 2, what we're actually calculating would then be 3 divided by 3. So we automatically shift this up by exactly the amount we need to get the expected result for rounding towards the nearest integer instead of rounding towards 0. Just remember this is the general formula. And as I mentioned, the most common situation would be if you divide by 2. So let's say a divided by 2. You want this to round properly, you just do a plus 1 divided by 2. That's the most common one. Plus 1 here, divide by 2 there. But you can do that for a lot of things. And you can twist it even further to something like b minus 1. if you want to always round it up. That's also a thing. So by changing the value in here, by adding a certain value, you can change the way it is effectively rounded. And applying that here, we can take our number. Before we divide it, let's actually adjust our code here, just for this one. Let's keep the original line up here. But we take this, we multiply by 5 still. But then the entire thing is added to 9 divided by 2, rounded towards 0, so 4. And we divide that by 9. So doing that here, plus 4 divided by 9, plus 4 divided by 9, plus 4 divided by 9. So we end up with 344 divided by 9, which, I'm just gonna fast forward, is gonna end up with a 38.2. Was it 0.2? 0.3? Can't remember. Well, it doesn't matter. In the end, the decimals are cut and we actually end up with 38, which is closer to the real value than a 37 would be. It's a minor adjustment that gets us a bit more correct answers. It reduces the error a tiny little bit. But let's say this is still not enough. What if we want greater precision? We want to measure less than 1 degree. We want to have the 37.7. Or maybe 0.77. Or 777. How could we do that? So let's say, instead of measuring just degrees, what if our unit is 10th of degrees? So 100 degrees Fahrenheit are 1,010th of a degree in Fahrenheit. We just change the unit, so to speak. Instead of Fahrenheit, this is 10th of Fahrenheit. So we have to adjust the formula as well. So this is not 32, this is now 320. We can keep these two values in, 5 and 9, and the 4, since they apply a ratio, they're proportional, so it doesn't matter if we increase these values or not. But for the addition and subtraction, it's important for these two. Keep in mind this plus 4 is only based on this number here. And we didn't change the 9, so the plus 4 doesn't need to change either. And if we did that, we have 1000 in here and 320 in here. So this takes 680. This would be 3400. Or this would now be 3404 divided by 9. And that would give us... Okay, let me just write this out properly. 37.8. Well, actually not 0.8, because the number itself would be just 378. But we know this is 10th of a degree. So this is actually 37.8. We just have to remember that our values are not in degrees directly. And of course we can just increase this as much as we want. Add some zeros here, add some zeros in there. And that way we can arbitrarily increase the precision here. More digits, more precision, more accurate values. as long as we keep track of how many zeros we added. We just have to somehow be sure about the specific unit we're using. This would now be thousandths of a degree. So thousandths of a degree might not be a very realistic use case for temperature, outside some very niche applications for scientific experiments. Let's talk maybe about time. So a different way to look at it might be in t. Let's say we store this in seconds, like we have a stopwatch going and we want to track how much time something takes. Well, maybe something takes 5 seconds, but we want to measure very accurately, not just in seconds, but because it involves a lot of electronic precision, maybe just measure how long a program takes. Maybe you want something more in the range of milliseconds. Well, then you would have 5,000 milliseconds, or maybe nanoseconds. We still measure time. We just measure it in a different unit. A unit that is using smaller increments, so we have higher numbers. So a rounding error, like we have here, becomes less and less pronounced. That's all we're doing here. We're just increasing these numbers so that the error we get is less proportional to the actual number. Before it made up almost a degree, but just by increasing it by 10, it made at most 1/10 of a degree. And if we go for thousandths of a degree, well, then we had a thousandths of a degree of error, which is negligible. I'm not sure there are many systems that can even measure that accurately. For time, this makes a bit more sense, since we do have systems that break down time into very, very small increments in very normal everyday objects. Like a computer clock internally is definitely using nanoseconds at some point. So your computer can definitely count in milliseconds and also nanoseconds internally, even though you're not really aware of it and rarely need to interact with it. Hopefully. There's a downside to this system though. It does give us more precision. We get more and more decimals. We just have to remember that there is a decimal point in here. We don't see it because it's stored as an integer number, but we just remember the first 3 digits on the right here are just the decimal places and the full number is on the left here. If we store something like 5 million nanoseconds to keep track of time in an integer, which only has 32 bits, we will quickly reach the end of how much time we can store on a single integer. Command integer, 32 bits, signed, so only 31 bits are effectively used for the number. That gives us an upper limit of, what was it? I think it was 2,040,000,000 something. I think that was about the upper limit, a lower limit for integer values we can store. So with nanoseconds, which are already a single second will have 1,000,000 of those, well, that means we can have about 2,000 seconds and nothing above, because the integer just can't store those numbers anymore. That's not even an hour. I'm sure you're gonna use a stopwatch at some point that has to run for longer than an hour. So how do we deal with that? Well, simple, just don't measure that precise anymore, right? Just drop a few digits, we only measure in milliseconds. And suddenly we can measure 1,000 hours, or at least a couple of weeks. That seems promising. So, depending on your specific application, we would just use a very small unit, so we can store big numbers and any error in the calculation gets relatively small. And if it's a really big number we have to store, that's very long time span, for example, well, we use a bigger unit, bigger increments, and that way we can store those longer time ranges as well. And because those numbers are pretty big, that rounding error is still relatively minor. If we're talking about a couple of thousand hours, then a single second or two doesn't really matter that much anymore. So conveniently, depending on your application, the error gets smaller or bigger by increasing the number, but it always stays equally irrelevant. Only there's now one more issue. What if I want to store time that can be both small and needs precision? Like, how many milliseconds does it take for my program to finish? But can also be very long running. Like, how long has my computer been on? Or what's the active runtime for this server program that technically has to be running 24/7? If we want to monitor that. What if we want to monitor both the total runtime of our server and the average execution time for a specific instruction in our program? We have to measure both the very small increments for how long is our program gonna take, and the very big numbers for how much time has the server been kept on for. I want to start with, what if we had another integer, let's call it e, which is just gonna be one number, like 1000. And if I have 5 seconds, I just have 5 seconds times, not d, e. And throughout my program, I just remember always to use this other variable e to pin down how accurate my units are. I'm just gonna say that t represents the number of time based on e 1/1000th of a second, or 1/10,000th of a second, or just 100th of a second. I'm using this variable to keep track of how accurate I am. And I can always reuse this variable in all my calculations without constantly needing to think about how many digits do I need in this constant, like up here. If I want to subtract 1 second from this value, from t, should instead of plus just write a t, that might be better. T equals t minus, well, I want to subtract 1 second. I'm not sure what 1 second should be. 1, 1000, 1 million? No, it's just 1 times e. Makes my life a lot easier. And if I have this e as a variable that keeps track of how accurate my values are, well, who says I can't just change this e later on? Maybe now I want something more accurate. Maybe this is gonna be 1,000,000 now. The problem would be my previous calculations with t don't really match up anymore. So I can't just overwrite e if I need to store a second time value with a different unit, with a different increment, I would have to define a second e. So maybe int t2 is gonna be dependent on e2. So we have t, which is going to be 5 seconds with an accuracy of e1000. And t2 is based on e2, so it's 2 seconds with increments of 1/1,000,000th of a second. And that means I can also combine these two numbers. If I want to add 1 second to, or if I want to add the number of seconds in t2 to t, well, we did that earlier. Just the number of seconds I want times the multiplier for e. And to get the seconds for the actual seconds in t2, we just divide the value in t2 by e2. So we could take, for example, t2, multiply this by e, and then divide by e2. I should just do this, might make it easier. No, whatever. And this part will magically take care of the whole logic. We just have the logic, this is number of seconds, well, this is a time unit, this is a time unit in seconds, sort of, a fraction of a second at least. And these are the representatives for how accurate are they, and by combining these two, we can cancel out the difference and everything will be taken care of. We adjust t2 to match t. This concept with these multipliers for our numbers, just to make them more precise, is a pretty common way to express numbers, very small numbers and very big numbers, in scientific notation. So 5 seconds, for example, are 5 times 10 to the power of 6 nanoseconds. This times 10 to the power of, it's quite common. And nanoseconds, this is a bit of metric knowledge in case you're not aware of it. We have seconds and the prefix, the specific symbol in front of it tells us another multiplier. Nanoseconds means we have the lowercase n, which is 10 to the power of -6, 1/1,000,000th. So this is in fact 5 times 10 to the power of 6 times 10 to the power of -6 seconds. These two cancel each other out, so this would be just 5 seconds again. And we can emulate this in our program by not storing e directly, but instead just storing the number of how many zeros do we want. The power of 10. So this was a 3, this was a 6. Makes everything a bit less clunky, a bit easier to see and to combine. This would not be e divided by anymore, this would be just minus or add, depending on what you do. Of course, that means we need to have the exponentiation now. We now somehow have to calculate 10 to the power of e2 or 10 to the power of e, which is not a built-in system that exists. But we don't need that either, because what we've done so far is all in decimals. But the computer is binary. The principle still holds true. If I just have a number, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0. Let's just take this number. This could be a normal number, full integer, but this could also be a number with decimal places. The full number up here, and a fractional part back here, the decimals. Or it could be up here. Could put the decimal point anywhere. Just because it's binary doesn't change the logic in any way. The only thing that's different is it wouldn't be times 10 to the power of something. It would be now 2 to the power of 2 to the power of 5, for example. The logic is still exactly the same, it's just a different base unit. And 2 to the power of is something we can do very easily in computers, because that's just a bit shift. And bit shifts, you've seen those in my assembly lessons. Just a reminder, if I have something like, let's not bother with a variable. Let's say I have just a singular integer value 1, and I want to bit shift this. There are 2 operators for that. You've seen this operator before. The angular bracket. This one for the lesser sign, 1 less than something else. The trick is we add a second one right after. Less than 0, for example, or 1 less than 1, 1 less than 2, and so on. There's also 1 greater than. This would be a bit shift to the left, this is a bit shift to the right. This is effectively 1 shifted over by 0, which is just 1. But if you shift it over by 1, you suddenly have... Actually, let's not bother with that. Let's just get to the result. 1, no shift at all. If you shift it over by 1, you have 1, 0. Shift it over by 2, you have 0, 0. And when you shift it to the right, you just get back to those values. That's a bit shift. That's basically exponentiation with a base of 2. Very simple operation, very cheap, very quick. So if we use the power of 2 for our little tracker, our e's here, we can very easily calculate a multiplier for our time values right now, t and t2, to keep the accuracy higher, to make the units not seconds, but milliseconds, nanoseconds, anything we want. We could also go in the opposite way and make those negative values, which just means the value gets smaller. Now, that is at least true for scientific notation. That doesn't work so well for integer values, because a 5 divided by 1000 would just end up in a 0. We're back at the original issue now. But it's generally possible to do this kind of stuff now. This concept is so very important in many programs. Sorry, I had to drink something. Is keeping accurate track of a number with a variable degree of accuracy for the sake of fitting everything inside very limited memory space. That C# has a unique type for that. Well, not exactly unique. There are actually several types for that, kind of. Let's talk some names first, some clarification. What we did first with our Fahrenheit, with the 1/1000th of a degree, or 10th of a degree, we just assumed this is 100 degrees, fixed, and we store the number just as a thousandth of a degree. We just imagine that the last 3 digits are decimal places and everything before that is the full number. That would be a fixed point number. Because the point, the decimal point, is in a fixed position. Always the last 3 digits are the decimals, in our case here. That's how we defined it, and that's how we used this number. Everywhere we used it, we assumed that's one fixed location for the decimal, and we can rely on that everywhere. Which has limitations, of course. So we switched to a different system where we can adjust the position of the decimal with a second variable, with a second value. And we can just freely change the way we represent these numbers through our program by using a different value here. Effectively, the position of the decimal was no longer fixed. It could freely move around back and forth. And one way to express that thought would be through the name floating point number. Because the decimal is no longer fixed, it can freely float back and forth to represent different units, different sizes of number. And that's where C# took its name from. For the name of this unit, or type, which is called float, for floating point number. So we can have a float D, for example, which is gonna store a number like 1. And this is perfectly fine. You can just store an integer number in there, but much more interesting, we just write down a dot in our program code. Just literally write down 1.2. And this is now 1.2. It's permanently stored in this one variable, which internally will keep track of this decimal. You can also make this 2, 3. No problem, 2 decimals. You can still store it. You can also have float m equals 123. Decimal is effectively here, we don't write it down, but it is there, kind of. Actually, let's make that maybe clear and just write out the 0. Doesn't really hurt. This 0.0, like that. And we can combine these numbers the way you're used to. D equals D plus M. No problem. The logic internally will keep track of how many decimals are in each number and will try to accurately keep the actual result in. Though it will always favor the general size of the number over the precision. So if you have a very big number and a very, very small number, if you add them together and it's too large to fit within the 32-bit a float can use, then it will drop the accuracy in favor of just storing bigger numbers. Float is 32 and it's signed. Of those 32-bit, we have 1 bit dedicated to just tracking down if it's positive or negative. It's not exactly 2's complement anymore, because floating point numbers are actually a combination of 2 values. Like scientific notation, just what we did earlier, we have a number and we have a multiplier, so to speak. We have the mantissa and we have the exponent, and I don't know what the English versions are of those names. Should be very mantissa? Exponent? I think their names should be pretty similar. I think German and English got them from the same source, so. But yeah, floating point numbers work differently internally. you don't need to really think too much about that. Just know 31 bits, 1 bit for signing, and was it maybe 20 something bits for the number, and the rest for the multiplier, the exponent. Can't remember. Those are details that rarely are important. And if a float isn't enough, a float is too small for your number, or not small enough for your number, when you have something very precise but small, then you can just increase the number of bits you use by 2. Similar how we can go from int to long to double the amount of space we have. We can go from float to double. Which also can just store floating point numbers. Just as float, it does use more bits, so it can technically be either more accurate or store more extreme numbers, just in general. There's more space to store data. There's also a different type that can store decimals, which is called decimal, but personally I find that type very weird, and I think it's only really used for something like currency calculation. I'm not too sure. I think decimal was an example of a fixed point number. And I basically never used that, so I'm not too sure what it's actually capable of. I'm fairly certain it was a fixed point implementation, so fixed decimal places, which can be quite important, depending on what you're calculating. And it has a lot of built-in options for converting numbers. But that's a different topic for later today. These are the types we can use for storing decimals. And with that knowledge, we can now go back to our little conversion up there and adjust the code one more time to maybe store something more accurate. One way to approach this, instead of integer, we're gonna declare those variables float when we create them. So we have a float c and a float f. The math is pretty much the same still, for the most part. And we calculate the result. Come back, please. That's better. We start off with the 0, and that's going to be 32. Then we overwrite that with 100. And then our last calculation happens. But there's something interesting here. Actually, we should start up there. That might already be quite good. Let's assume we already did the first instruction, and now we are looking at the second one. Float f equals c times 9 divided by 5 plus 32. First operation was the multiplication, where we look up c and multiply that with 9. Well, we have already the micro operation of looking up the value, c, which we find up here. It's a float and it has value 0, or 0.0 if you prefer that, to make it clear as a floating point number. And we multiply that by 9. Simple, 0 times 9 is 0. But the computer doesn't see it that same way. The computer doesn't see a 0 multiplied by 9. The computer sees the operation called multiplication, which receives two values, the float c and this 9. C# is drilled to assume a number is an integer. So what's actually happening here is we have, after looking c up, float multiplied by int. Two numbers. So we can multiply them, sure, but the computer now sees float times int. It sees two different data types that are trying to get mixed using specific operation. The computer does know a multiplication if it's just two floats. And it also knows multiplication if it's two ints. Those are fine, but it does not understand operation multiplication if it's getting a float and an int. It is that specific. We see multiplication and we just apply it. Doesn't matter what number it is. Those are just numbers. But to the computer, float and int are different things. It doesn't understand the concept of both are numbers. Just combine them as any number. And it's good it does, because the way the float is structured internally, how the bits are arranged and what they mean, is very, very different from how an integer operates. So you might have hardware for multiplying integers, like actual circuits on your chip, on your CPU, your ALU, wherever you put them, that can multiply to integer values. And you most certainly have, in any somewhat modern hardware, special segments that can deal with floating point numbers, because the internal format is also pretty common and standardized, so you have actual hardware for that. But multiplying a float and an int means you have to interpret their meaning separately and then somehow try to mix them, which is weird. It's very difficult. Now imagine you have other data types as well. We already had something like short, maybe. Short times long also doesn't exist, because if you imagine the computer just looks at an operation and tries to execute that, we would have to define what multiplication means for every single combination of data types, because that influences the outcome. Not just one type with one type. We also have to include the reverse, so something like int times float could be completely different from float times int. Keep in mind, division, it makes a difference in which order you put them, or subtraction. The order of the numbers, the arguments for the operation matters. So if we suddenly allowed a mix of data types for a simple operation, it would mean we would have to define how this operation works for every possible combination of types. That's just too much. So we can't mix them. This is not possible directly. There's a simple workaround though. We can't just mix float and int in a multiplication. But we can do float times float, and we can do int times int. So to solve this problem, we just don't multiply these two, we simply multiply an integer with an integer, or a float with a float. It's that simple. The only issue is, in practice, we get situations like this where we don't have a float and a float, or an integer and an integer. luckily there's a way around that. We just change our program so that we do have two equal types. I could turn this 9 into a float. Can just add a little f after that. I'm actually just writing the letter f directly after the number. And now the computer knows that this 9 isn't supposed to be a float, isn't supposed to be an integer, it is now a float. Instead of interpreting this 9 as the integer value 9, it's interpreting this as the float value of 9.0. And now we just have a situation of float times float. And it can actually calculate that. Alright, let's go with that route. That seems doable. So we have the float f equals 0 times 9. Both are floats, so we can multiply, which is just going to be 0. But specifically, it's going to be a float. Float times float results in a float. Integer times integer results in an integer. And we divide that by 5 and add 32. Now we have 0 divided by 5. But again, on the left we have a float, the result of this multiplication. And on the right we have 5, which is interpreted as an integer. So, sure, we could change our program once more and turn this into 5f again, to make clear that this is a float. But maybe we don't want that. Maybe we are too lazy. Maybe we don't want to go everywhere and turn this into a float by hand. That's not an issue. The computer will do that for us. Well, sort of. The computer will still treat this as an integer. When we write our program, this 9 is a float. We told it that. It will see this 9 as a float. But this 5 is still just integer. Data type int. So we end up with float divided by int. What the computer can do now is it will convert this value 5 from type integer to type float. Because data types can be converted between one another. You can, just like we did earlier, turn a 9 into a float just fine. And the same, we could turn this 5, which would be seen as an f, as an integer, with a single f into a float. There's no problem converting between two different number types. Just going from integer to float, why not? It's still just a number. So the computer has built-in routines that generate a new value. It's not a simple bit operation. It is a bit more complex than that, but you can just turn integers into floats. And because that's so easy to do and comes with no downsides, the computer will look at this, see float divided by 5, will understand that I don't have an operation that can divide a float by an integer, but I could just convert this integer to a float without any downsides, and then I would have float divided by float. So the computer is just going to do that. It's not treating the 5 as a float. That's important. Up here, we converted the 9 into a float. The 9 in the program itself always is a float. There's no conversion necessary. The 5 is in the program an integer. But during runtime, the computer will understand this is float divided by int. And it will convert that to a float. So it will convert this as a step in between. It's like a micro operation again. It is pretty much a micro operation. We just don't see it. Just like we look up C first here to get the calculation going, we also have to convert 5 from int to float. and then it will make the full calculation happen, which is going to be, again, 0. F for float, plus 32. And now we have another operation which combines a float and an integer. And again, the computer doesn't have that operation, but it knows it can just convert an integer to a float with no downsides. And then we have a float plus float, which is an understood operation the computer can do. So we end up with float f equals 32 f. So again, it's first converting the 32 to an f and then calculating the result. It is taking the integer, converting it, and then calculating. The 9f here is something we declared beforehand to be in float already. No conversion happening here, conversion happening automatically here. So after all of our instructions are done, or at least that instruction is done, all our operations are done, we have a float f 32.0. And now maybe I should add these as well, now that you know that exists. That is a float. Which, by the way, is happening up here already. This very first operation already has that issue. Because this is a 0, which the computer assumes to be integer. And we're trying to assign an integer 0 to a variable that stores float. Not possible. This is integer, this is float. You can't assign a value of one type to a variable of a different type. This doesn't work. Not allowed. But again, the computer knows that integers can just be casted to float. And that's the term we're looking for, casting. This conversion specifically for changing the type of a value is a cast. And a 0 converted to a float, a cast to a float, can be assigned to a variable storing floats. I could start my program by just writing an f in here, so the 0 would be a float already and no cast needs to be done. In our case, technically we started off with the integer 0 and it would need to cast it. Generally, compilers are pretty damn smart, and even though we didn't write this out specifically, the compiler will assume, yeah, you actually meant to use float in here. I'm not going to cast it during runtime. I'm just changing the program to use a float already in here. That's the compiler's doing. You don't have to worry about that. But strictly speaking, that would happen first. Then we would change our program here. Again, it's a 100. Strictly speaking, an integer that would need to be cast during runtime into float to be assigned to a float variable. Again, compiler is smart and will automatically kind of declare this a float in the program code without us knowing about it. But end result would be a floating point number 100 in memory, and then this long operation happens. And all the same rules apply as above here. We have a float minus integer, so it will convert the integer, will cast it to float, and subtract it. Result is a float, which is multiplied with an integer. The 5 is cast to float from integer, multiplied, and result is a float. Add an integer, cast float, and result is float. Divide by 9, cast from integer to float, and result is a float. And we store the correct value in C. Though this time, because this is now a floating point number, this very last step, this division by 9, is actually doing full decimals. which means we can drop this. We don't need to round anymore. We don't need to change the rounding rules, so the +4 can go. And we just have a 37.777 something 8. Keep in mind, the actual number here would be 0.7 repeating. The floating point numbers do have a limit. They can't store infinitely many decimals, so at some point they will cut it off, and usually that's by rounding it. Or it will look like rounding, so 0.8 will appear at some point. How many decimals you can store depends on the type. Floating point numbers work the same regarding a float or double. It's just you're gonna have some more decimals in a double than you have in a float. Still way more precise than we would ever need for a temperature. For human body temperature ranges that are still recognizable as human bodies. I think 1,000,000 degrees, that's not a human body anymore. Maybe a sensor malfunction. Let's try something. Int L. Equals C. Int L equals C. We have two operations. We have the declaration of a new variable and an assignment. Declaring a variable, sure. We have integer L starting with nothing, just declared. And then we have the assignment. And now we have another clash. We have two different data types. C is a float, and we try to assign it to L, which is an int. No problem, right? We've did the same in here and everywhere in between. We can just cast the C before assigning it to L to integer, right? Just as we cast from integer to float, we can cast from float to integer, right? It's just a number. True, we can, but the computer won't do it automatically this time. Because we are right back at the very beginning with the initial issue of this number cannot be stored in an integer. We can't store the decimals. And the computer understands that this number, the C, can store more data than this variable L can store. Well, technically more data is the wrong term since both are 32-bit numbers, but there's a different set of numbers that both can store, and generally a floating point number cannot be safely stored in an integer without dropping the decimals. Would have to round again. Have to ignore all the precision we worked up for and round towards 0 once more. Which is absolutely doable, but we have to explicitly tell the computer that it's okay to do so. Going from integer to float, generally you don't lose anything. Technically, yes, there are numbers that can't be accurately stored in a float, but they are still pretty close and it's treated as good enough for the computer to just do it on its own. But from float to int, this is most likely gonna lose something. There's a reason you use float after all. Either those numbers are extremely big, way bigger than anything you could store in an int, or they are extremely precise with decimals, which are definitely not something an int can store. Converting from int to float technically can lose something, but is likely gonna be fine. But going from float to int will most definitely lose something. And you have to tell the computer explicitly that you are okay with losing data. That you made the express choice to drop that data. This would not be accepted. The compiler would flag this and you can't just cast float to int. except you can just cast from float to int. The way that works is the same way any manual casting works. That sounds weird. But the way you cast in C# in general, no matter what types you're using, you have normal brackets which contain the type you want to cast to. So in our case, we want to go for integer, and then we close the brackets again. So we have just the type we want to cast to, we want to convert something into, in normal brackets, directly in front of whatever we want to change to that type. A value, I could explicitly use a default 0 float. I could also use just an integer, that would be fine as well. Casting integer to integer is fine, nothing happens. I can also use our C, a variable. This is an operation, this entire thing. This is a cast. More specifically, this is an explicit cast. Casting in general is just converting between different data types. And in cases where the computer is fine with doing that automatically in the background because we don't actually lose something, it's fine to do so. That's called an implicit cast, because you imply it's fine. You just write the code, we have floats in here and integers in here, and the computer knows, no, it's fine to cast. I'm just gonna cast this to a float and make my operations happen. That's fine. But in here, where the computer doesn't accept it on its own, we have to explicitly cast it. We have to tell the computer explicitly, please change this data type, we accept the data loss. Or the potential data loss. It could be that we don't have any decimals and we as programmers know the values that come through will not actually lose something, so it's definitely okay. But we have to tell the computer that. We accept any responsibility for errors that result from this cast. And then the computer is happy to do so. It will take the original value, C, which is a float, and it will then convert this value into an integer using some specific rules that depend on the types you cast from and to. You can't cast everything. The computer has to have rules that describe how that happens. Again, floating point numbers and integer numbers work very differently under the hood. The bits are arranged very differently and have very different meanings, so you can't just flip the data and just say this is now an int. I mean, technically you can't do that, but it's not going to represent the same number. It's going to be some nonsense value. So there needs to be an algorithm that decides how the numbers can be transformed from one type to another, and not for everything there is an instruction or a set of instructions that the computer can use to make that transformation happen. For most default types, so especially for all the number types, that just works. If you have two numbers, float, double, int, long, short, byte, whatever, you can just convert back and forth just fine. Assuming you do an explicit cast whenever you might lose something. So this C gets converted to an integer, which just means drop the decimals. So we have now a 37. And then we can assign it to an integer and end up with 37. 37. And that's what we have in L now. There would be no issue with casting explicitly from an integer to a float. You can make this operation explicit. There's no reason to do so, but you can do that. That's fine. Generally, explicit casting can be always done. The outcome might not always work correctly, and if the computer doesn't understand the instructions or they simply become impossible, it will complain. But in many cases, like this, we can just leave that out, and the computer knows it is technically still there, but it's fine if I just cast it on my own. I don't need you to tell me that it's fine. And as a side note, this is not only for the conversion between floats, for floating point numbers, and int for integers. This is also true for converting internally between, for example, shorts and integers. Short was only 16-bit, so way less range for storing numbers than integer with 32 bits. An integer will always be able to store anything a short contains, so this is fine. But a short will not always be able to store the number an integer can contain. So this cannot happen. If you want to do this, you would have to... short. You would have to explicitly cast it. Same with double and byte. In case of floating points, it's not just the range, it's generally all about the range of numbers. The integer types, the less bytes you have, the less the range you can store data in. You can always go bigger, that's fine, that's implicit, but you can never go implicitly down. You have to explicitly tell the compiler, drop the rest of the bits, just store what you can, what fits inside this smaller variable. And for floating point, it's not just about the size, it's also about just you lose precision. Any decimals are lost. It's not okay. So you have to explicitly tell the computer, just do it anyway. And some conversions will, even if you do it explicitly, not work. So a bool B doesn't work. And I'll see, what kind of music is this? Let me just advance the playlist a bit. That's a weird track. Kind of dramatic. So bool I, we have an integer value we want to assign to boolean. Doesn't work. For one, boolean technically represents only a single bit, an integer 32 bits, so definitely we lose information. But conceptually it's also about, they work very differently. The boolean is not a number, it's a true or false value. You can interpret that as a single bit, as a binary number, but that's just a way to interpret it, that's not what it represents. So I could do bool I and explicitly force it to cast, and the computer would just, no, deny it. It will cause an error. I cannot convert an integer into a bool. It's just too weird of a type difference. There's no instruction that tells it how to do this. You can later on, however, make up your own rules for what's possible and what not, especially once you start making your own data types. And then you can make up algorithms that tell the computer how you can convert between different types. And you decide if the computer is allowed to do that on its own or if a programmer needs to do that explicitly. Yeah, this is not okay. Now let me think if I forgot something, but I think that's all we had to cover today. Oh, maybe, since I see this up here, maybe one last hint. Not directly related to our types, but kind of involved in the general topic. This algorithm is actually kind of a newbie trap. I've seen this as an exercise for new programmers, and in a slightly different context, doesn't matter right now. But the reason I love this specific one is it's so easy to make a mistake. If you present the newbies just, here's the formula for how you can convert between these two units. And you arrange the example of how that works in a different way. Most of the learners will also write out the formula in code the same way. I started by using the temperature that I want to convert and multiply that and divide and whatnot. Something interesting happens if I would if I just have integer values, int a equals 10, like that, and then go int b equals 2 divided by 3. Something simple like this. Perfectly fine. I mean, sure, it's integer values, so we know that this division by 3 will lose decimal points and it will be rounded towards 0. That part you understand now. So this would be 10 divided multiplied by 2 is 20, divided by 3. That would be 6.2 repeating. That would be dropped, so we end up with just 6. Just 6. If we add a +1 in here, using that standard rule we talked about in the beginning, that would turn it at least into proper rounding and we would get to 7. But that's all that would happen. We just have a small rounding error, basically. If you present the question differently, they might start writing something like this. It's the exact same formula. Mathematically, it doesn't really change much. I mean, you might want to add brackets, but in this case, operator precedence, it doesn't matter if you add the brackets, just makes it more clear. Thing is, same result, technically, from math standpoint, but very different result when executed as a program. Because operator precedence, we start with this division and then do this multiplication. We go from left to right. And because we do 2 divided by 3 with integer divided by integer, that means we round towards 0. What is 2/3? Round towards 0, it's just 0. Times a is always going to be 0. So the newbie trick is that they start to wonder why any input they give will always result in b being equal to 0. Which holds still true even if a would be a float, which is one of the first things they will try. Make this a floating point number so it can store decimals, and make this a floating point number so it can store decimals. But it will still be 0 because those two are by default treated as floats, as integers, not floats. So we still calculate integer 2 divided by integer 3, which will result in a 0, which is then implicitly cast to float to be multiplied with this integer a, but still to a floating point number 0. So that's why newbie killer, the way I presented it in the beginning here, I put the variable first and multiply it first. That way we only have the rounding error and didn't have to think about the implications of this actually being always 0. Specifically this would not be quite right, and this 5/9. If we actually drop those brackets now. 5 divided by 9 would be 0. So if you put that in front, you would always end up with this being 0. Actually, another thing, this 2 divided by 3 doesn't actually happen in runtime, usually, because the compiler sees this as a calculation that can be done before shipping out the program. If you have some simple math operations, like this, the compiler will just calculate the end result and store that as the constant value we put in A in our program. So these two operations don't happen at runtime anymore, they happen when you compile your program. Same way this 2 divided by 3 will happen during compilation and just store a 0 permanently in the program. Just optimizations the compiler does. Just thought that might be nice to know. So it's no problem if you have some weird constants, if there's some values that are derived in a weird way, you might want to write this out completely so it's clear how those values are generated. The compiler will optimize that anyway into a single number. And only, oh yeah, one last thing. Just as these numbers are by default treated as integer by the computer, if I write down 0.0, these are no longer treated as integers. The decimal is respected. The computer knows this is a floating point number, but it doesn't default to float, it defaults to int. To double. So integer numbers default to int, and floating point numbers, anything with a decimal, will default to double. So if you have specifically a number in here that you want to have with the decimals, and you need to float, just add the f in the end. So the compiler knows you do want a float and not a double that needs to be converted back and forth and whatnot. Also, there are other shortcuts, so you can double W print 4. You can just store this as a number. It's a this will be treated as a number with decimals, so it's by default a double already. But if you want to declare something as specifically a double, you can add a D in the end. So F for float and D for double. You also have, okay, I already have an L. P. L for long. Not every data type has these, but they're useful to know. L for long, D for double, F for float. You might need those shortcuts from time to time. Or those little postfixes to make clear that a number is a certain type without worrying about some weird warnings or errors by the computer because types don't match. That's a quick fix around something. And with that, we are truly done for today. Different data types don't mix by nature. You have to always make sure that an operation applies to the exact data types that it was defined for, which is usually the same data type on its left and right for at least some basic numbers. And if that can't be done, then one of the numbers has to be adjusted to match the other, or maybe both have to be adjusted to match one another. And you always have the option of implicit casting, which the compiler has some rules for. Some types can be implicitly casted into another, usually when there's zero data loss or close to zero, or when it's essentially treated as you don't lose data. And you have explicit casting when the computer doesn't think it's safe to just change this number to another number because you might lose information. In that case, you have to explicitly tell the computer to do that. And even if you do that, the computer will try to do it and then realize I don't actually have any idea how to do that, and it will break during runtime. Those are problems for way later though, when you start making your own stuff. And with that, we're done for today. Have a nice Sunday. See you next time.